And I also want to thank Jay. And I also want to thank Jay for the invitation. So the title of my talk is Practical Structure of Conventional Neutral Atmospheric Boundary Layers. And this is a seminar about intelligent and bio-inspired mechanics. But my topic is about atmospheric flows and also wind farm flows. So I assume most of you are unfamiliar with the basic concepts about the atmospheric boundary layers. So here I want to show you first a short movie. This movie will introduce the basic concepts involved in ABL flow. Okay.
Have you ever experienced that moment before landing when the plane shakes? That's when you're entering the atmospheric boundary layer, the layer of the atmosphere nearest the surface of the Earth. Sometimes you can see it from the top of a mountain, as the underlying misty layer that contains smog, or from the sea when the clouds seem to be sitting on an invisible surface. At night, and on cold days, this layer can be as thin as a few dozen meters. But in hot weather, especially in summer, it can extend to over 2 kilometers above the surface. It all depends on heat. During the day, the sun heats the surface of the Earth, which reacts like a stove heating a pot of water. Bubbles of hot air form and float up above the cooler surrounding air. Then these bubbles rise, carrying dust and moisture with them, and create larger bubbles that may cause clouds to form. Then, as night falls, it is as if the stove is turned off. The mixing stops, and the layer near the ground cools down. In some cases, fog forms, because the air in this layer is saturated with moisture. But the surface is much more varied than a pot of water on a stove. In a city, paved areas heat up faster than green areas, while oceans, seas, and lakes heat up more slowly than land. In the mountains, across ridges and valleys, the boundary layer is very complex and the movement of the air is difficult to predict.
Okay, so what's the atmospheric boundary layer? And it's the layer of the atmosphere that is nearest to the surface of the Earth. And from the video below that, the boundary layer can be classified like a daytime ABL and a nighttime ABL based on the heat on the surface. Okay, and because we humans live inside the ABL, it has a significant impact on our daily life, like the aviation, agriculture, air pollution, and wind energies. And because the complex interaction between shear stress, buoyancy force, and collision force, as well as like a complex terror effect, the ABL flow is very difficult to predict. So what can we do? And to analytical study the ABL flow, we need a more detailed classification about the ABL. And in the movie, they classified it into like a stable case and a correct case only based on the condition on the surface. But however, the top boundary condition has also some important effect. For example, for the neutral case, when the surface heat flux is zero, and when in the free atmosphere there is stable stratification, then this kind of boundary layer is called a conventional neutral ABL flow. And most of study focus on truly neutral case, but we found, or recent study found, the free atmosphere stratification has a significant impact on both the ABL flow and the wind farm flow. So in this talk, I will focus on conventional neutral ABL. So what's the basic characteristics of CNBL? It has two characteristics. First is the surface heat flux is zero, and second is that the free atmosphere frequency is greater than zero. And to simplify the analysis, we need to make some other assumptions. And among these, I think the most important assumption is about stationary and horizontally homogeneous collision. And here is a sketch for the ABL vertical structure. And we want to load the wind profile, especially like the wind speed profile and the wind angle profile. And this is because these two variables are very crucial in wind energy applications. So why the ABL flow is so important in wind energy? And this is because, like here shows, the power output of a wind turbine is proportional to cubic of the wind speed. And thus, in a recent paper published in Science, the authors stated that understanding ABL flow physics is one of the great challenges in wind energy science. So the first question I want to answer in this talk is how to predict the wind speed profile. So when talking about wind speed profile or the velocity profile, what came to my mind first is the famous log law. And this law is derived first by like Prandtl and von Karman. And this law is based on several assumptions. For example, it is assumed that the velocity scale can be taken as the friction velocity, and this velocity is taken as a constant through the boundary layer. And on the other hand, the length scale or the mixing length scale is taken as the coordinate. And in addition, we don't consider the thermostratification case. In this term, under these assumptions, the velocity gradient can be writing like this. It is okay, like this one. Then by integrating, we can get this log law. And here we know that if we actually the log law exists in almost, I think, in almost a very wall-bodied turbulent flow. For example, like a pipe flow and the flat plate boundary layer flows. And in wind and in practice, when especially in wind energy application, if we want to use the log law to predict the wind speed, we need to load two parameters. First one is the friction velocity, and the second is about the roughness height. So how can we determine the roughness height? Usually, the roughness height is determined only by the properties of the surface. That means we can measure directly in field measurement and one condition. So it can be directly used when the wind condition changes. However, in reality, the situation is more complicated, especially in overseas, because overseas, the roughness height may depend on the wind speed. But in this talk, we will focus on the former case. That means we will take the roughness height as a low quantity. So another question is how to determine the friction velocity. In micrometeorology, it is usually related to the geostrophic wind. So the geostrophic wind is the wind above the boundary layer, like here. So it is usually related through the so-called geostrophic drag law. Actually, this law also exists for like a pipe flow. And this, the GDL law was derived first for truly neutral case. And in this case, the coefficients A and B are universal constants. However, in the CNBL case, the system are governed by two dimensionless parameters loaded, only one. And one is like the rho speed number, and this number also exists for truly neutral case. And another one is the identical number, and this one is a new parameter appears in CNBL case. So in this case, A and B is not a constant anymore, but functions of the I. And suppose if we load the values of A and B, then we can use this equation to determine the friction velocity. So so how can we determine the values of A and B? So first we make some comparisons between various length scales involved above the surface layer. And here Ln is the external stability length scale, and there is the altitude, and Lf is the rotational length scale. It shows clear that the Ln is the smallest length scale. So then we assume that the velocity gradient, and when normalized by the U star and Ln, is only a function of the normalized coordinate. And here, and h is the boundary layer height, and it can also be normalized by the Ln, and it can be parameterized very well with this relation. And here, the solid line is the theoretical prediction or the model prediction, and this blue squares are the atmospheric data, and these triangles and circles are numerical simulations. So this means the boundary layer height can be parameterized very well. And the left finger shows that confirms the assumption because it really shows the normalized velocity gradient, and it shows clear that all different cases match well above the surface layer. Okay, with these assumptions, then we integrate these equations. Integrate the velocity gradient from the top of surface layers up to the top of the boundary area. Then after some algebra, then we can get the expressions for A and B. So in summary, is to determine A and B, we only need to know 3 empirical constants. That's A1, B1, and C1. And all these constants can be determined like a least square fitting based on high fidelity database. So we did this by performing a suite of large eddy simulations. And here shows the comparison between the model prediction and numerical simulations. Okay, the agreement is really, I think, is really well. So since we determined the values of A and B, then we can use the geostrophic drag law to determine the values of like the friction velocity and the total wind angle change across the whole boundary layer. And it also shows clear that as the free atmosphere stratification effect increases, the friction velocity is reduced while the total angle change increases. So, okay. So now we already know the 2 parameters involved in the log law. Then we want to know the performance of the log law in the prediction of the wind speed profile. Here shows the LES data of the wind speed profile. And here is the prediction of the log law. It shows clear that the log law agrees well with the numerical data, but only inside the surface layer. That is about 10% of the CMBL. Why the log law doesn't work well above the surface layer? And we think it's because these assumptions, and because we assume the momentum flux is constant throughout the whole boundary layer. Of course, it's not true because it is an approximation inside the surface layer. And we also assume the length scale in the whole boundary layer is the coordinate. But this is of course not true because for at least near the top of the boundary layer, the length scale should become 0 as there is no turbulence above the boundary layer. And in addition, we didn't consider any buoyancy force in the classical log law model. So how can we extend the log law above the surface layer? Here I want to introduce 2 previous works. The first one is given by the Greening in 2007, and the author observed that the length scale in different regions is different. For example, in the surface layer, the length scale should be the coordinate, and in the top of bottom layer, length scale should be in h minus z, and in the middle of the bottom layer, there is larger length scale. So they proposed, okay, then we can use a generalized mixed length like this. And they also noticed that the U star, I mean the friction velocity, is not a constant. So they proposed to use this linear profile. This automatically certified that in the surface it equals to U star surface. Okay, and on top of the boundary, the U star is equal to 0. Then based on these two modifications, they got the so-called Green model. And now it includes two terms. The first one is the classical log term, and the second is a correction term. Here, the length scale in the middle of bottom layer is not low yet. So to determine this parameter, we need to combine with the GDL law. That is by setting the wind speed on at the top of the bottom layer equal to the geostrophic wind speed. And here is the performance of the Green model. Okay, and compared to the log law, yes, its performance is better than the log law. However, in the case still not capture well the profile of the wind speed, especially this shape. And we call it this shape like a low-level jet, because you see there is a peak. That means that this peak means the wind speed is larger than the geostrophic wind speed. So there another way try to extend the log law above the surface layer. That is by accounting for the line uniformity of the temperature distribution. So this, for example, Kelly in 2019 tried to collect the heat flux profile to the wind speed profile, and they try and get two results. First, they proposed a profile for the heat flux, and then based on this heat flux and dimensional analysis, they proposed such a model for the wind speed profile. Okay, and here is the performance of the Kelly model and mean. You see, about 0.7 of the dimensionalized coordinate, its performance is better among these three models. However, further above is it deviates significantly from the real case. So why would this happen? We think it's because they made they make a very crude assumption about the heat flux, because they think the heat flux is a linear profile. Actually, the heat flux profile is not linear. In here, collected all numerical results as well as others, and it shows clear that the heat flux is linear only in the lower part of the bottom layer, but in this region we call it the inversion layer. They will change rapidly. So if we want to improve Kelly model, the first thing we think is to propose a more accurate heat flux profile. So how can we do this? First, based on dimensional analysis, we noticed that the heat flux, when normalized by like Ln, the external stability length scale, and the friction velocity U star, and the beta is a buoyancy parameter, then the heat flux should only be a function of the normalized coordinate. Okay, So, but how can we determine the expression for this one, like a pi1? We notice that, okay, in this part of the the heat flux is a linear function of the coordinate. So its slope should be a constant. And we also notice that in this layer region, it changes sharply. And this reminds us that how Pareto got his border layer theory. So that means there must be a high order term multiplied by a small parameter. And the physical meaning of this small parameter is very clear because it just represents the ratio of the inversion layer thickness over the whole border layer thickness. Okay. And this is a second order ODE. And to solve it, we need two boundary conditions. The boundary conditions comes later because the heat flux is zero on the surface and on top of the boundary layer. So the solution for this parameterization equation comes and it looks like this. And here is the prediction of the model. Clearly, it captures the whole profile of the heat flux very well. So now with the correct heat flux profile, how can we get a more accurate wind speed profile? And to do that, I want first review very quickly the famous Monin-Obukhov similarity theory. And this is in this theory, basically, I mean, the velocity gradient should be like this, and in neutral case, phi m equal 1. So this is then we can get the log, but when the surface is heated or cooled, then there should be another term and phi m, and it is called the thermal stability correction function. Okay. And therefore, I mean, the expression of phi m can hardly be determined theoretically. So basically, people determine the form by fitting based on high fidelity field data like this. Anyway, the final expression for the wind speed can be expressed like this. It also includes two terms. The first term is log term, and second one is expressed by psi, and psi is only a function of the stability parameter. And here, L is the Obukhov length scale, and it is defined based on the heat flux on the surface. And for neutral case, we know that the QS equals 0, that means L equals infinity. So that psi always equals 0. That means in neutral case, the most reduced to the log. So how can we use the idea of most to get a more accurate wind speed profile that is varied in the whole boundary layer? First, we assume the wind speed profile can like most written in this form, but in contrast to most, here we define L using the local heat flux rather than the flux on the surface. Okay. Then to determine the form of psi, we assume that the simple power law of psi, and it can be written like this. And so we only need to determine the power exponent. And to determine P, we further match up this model with the gradient model in the surface layer, and we notice the L. You see L100. I mean, here the inverse of L equal like a pi1, and we know that the pi1 in the surface layer is a linear function of the coordinate. So we can determine that P equal 0.5. Therefore, we can get our wind speed profile, and it looks like this. And here is a prediction of our model. Clearly, it matches very well with the LES data in the whole boundary layer. Of course, there is some small difference in this inversion layer. But anyway, its performance is the best among these available models. So our last question is, how can we predict the wind angle? Because the wind angle is the arctangent of the V over U. So to determine alpha, we need to know the profile of U and V, not only the wind speed. Previously, like in 1974, people already proposed some model. And this is basically using eddy viscosity approach. And it can be written like this. However, there are two drawbacks in this model. First, the author assumed a constant dimensionalized eddy viscosity. And of course, this is not true. And second, they assume they only consider they assume the turbulent shear stress vanishes in the below the inversion layer, lower and top of the powder layer, and this of course is not true. So how can we get a more physically reasonable and more accurate profile for the UV throughout the whole powder layer? We directly assume that based on our wind speed profile, we can assume like the stringwise velocity U. And when we're talking about the U and V, actually we are in this coordinate. That means the U is in this direction such that the tau, the shear stress in the surface is parallel to the stringwise, and so V is sparewise. For the U, there are two terms. The first term is a log term, second term is FU. For V, there's only one term is FV, and we assume FU and FV are regular functions. By regular, when cosine tends to 0, FU and FV tends to a finite value, not infinity. Okay, and for this form, we require that the wind speed, the wind is 0 on the surface, and also the wind and top of the boundary layer should be the geostrophic wind. And then we can get this, then we can get the boundary conditions for FU and FV. So based on the boundary conditions, we can first assume the form of FU and FV. And here, what we don't know yet is psi, but we require psi on top of the boundary layer and on the surface of the boundary layer equals 0, such that by FU, FV automatically satisfy these boundary conditions. Okay, so but how can we determine the form of psi? And because we think we want to collect we want to reveal the heat flux contribution to the wind profile. So, and we also know that the heat flux automatically satisfies this boundary condition. So we choose psi as the heat flux profile like this. We already know that. Then to determine the wind equivalence, we still need to determine the values of A psi and B psi. How can we determine this? And then we need to another condition. And to do that, we need to recall the Ekman equations. Okay, and this is Ekman equations. And these equations are satisfied by any ABL flow as long as the flow is in stationary state. Okay. Then by integrating the Ekman equations from the surface to the top of the bottom layer, we can get this like integral constraints. And then by substituting the FU, FV into these integrals, we can determine the values of A psi and B psi. We note that all these parameters, I mean all these coefficients, are only functions of the analytical number, and here directly compares, and here the results confirm this assumption. So now we can directly compare our model with the numerical simulations. And here it shows first the wind speed profile, and it shows clearly that the wind speed increases significantly as the Rossby number increases, and this can be revealed very clearly from this equation. In contrast, we found the normalized wind angle is nearly independent of the Rossby number, but it can change significantly as the I increases. Now we also now we know the wind profile. Then we can also we can solve the Ekman equations to get the profiles for the turbulent shear stress. And here we once again to list the Ekman equations here. And the right-hand side is nothing but the geostrophic wind deficit. And we know that the wind speed itself depends both on the Rossby number and the analytical number. But however, for the geostrophic wind deficit, it only depends on the analytical number and is independent of the Rossby number. For the Ekman equations, we have these boundary conditions that like this. That means the tau is to recover to 0 on top of the boundary layer. Okay. Then these equations can be directly solved. And here is the expressions for the turbulent shear stress. Similar to the geostrophic wind deficit, the normalized turbulent shear stress are also independent of the Rossby number. To check the validity of our model, here we compare the numerical, the theoretical prediction, and with the field data and the numerical simulation data. And here shows the geostrophic wind deficit profiles, and the solid line, the theoretical prediction, and the red circles are the numerical simulations, and like triangles and squares are field data. And clearly, the agreement is very well. Here shows the comparison for the turbulent shear stress, and again the model prediction and the field data and numerical simulation agrees very well. Now we have enough knowledge about the CMBR flow itself. So we want to ask, can we use this physical insight to develop some kind of wind farm model to predict the power output? And this is the topic of here. So here we consider an infinite large wind farm inside the CMBL. And previously, like the Upcut and the Porto Angle, they proposed a model for this kind of wind farm flow. Usually for wind farm flow, people will use like a top-down model. That means they will assume below and assume log below and above the half height, like this here shows. And because for CMBL flow, we already know that the thermal free atmosphere thermal certification can accelerate the flow. That means the real wind speed is larger than the prediction of log. So the author uses the correction term plus AU there to account for the thermal stability contribution. And also, they assume that this log law, corrected log law, is valid up to the top of the boundary layer. So here is another condition. And with this, and also with these equations, then we can get the half height velocity and also the power output. But we know that we know that the log law itself works very well in the surface layer, and we also know from wind farm flow physics that the turbine will slow down the wind in the turbine regions. And we also know that the log law is not valid, valid in the whole boundary layer. And we also, from this situation, we know that the Obukhov model works only for didn't consider the effect of turbine layout. That means, for example, staggered and aligned. Based on this argument, we propose our own model for wind farm in conventional neutral boundary layer. And here, below the half height, because the thermal stratification in free atmosphere has negligible contribution, then there is only a minus term to account for the drag slowdown effect by turbines. And above the turbines, slowdown effect is more or less balanced by the thermal stratification acceleration effect. So we propose these two equations here, and we also introduced the factor beta. It is called the flow inhomogeneity factor to account for the layout effect. And for the thermal stability effect, it is accounted for by using the geostrophic drag law. Okay, here is the main idea of our model. But before using this model, there are two questions we first need to answer. First one is because the wind turbine or wind farm can change the flow significantly. So does the geostrophic drag law still exist when extended wind farm presence? And if yes, should the values of A and B be the same as low turbine case? And second is, how can we determine the value or predict the values of beta and the value of AU? So for the first equation, we performed a series of numerical simulations. Basically, we performed 6 cases. And here is the results. And from these two figures, we can get two conclusions. First, we notice that all symbols collapse to the solid line. That means that the geostrophic drag law for extended wind farm still exists. And the second is we notice that the dashed line is significantly different from the solid line. That means that the values of A and B for wind farm case is totally different for the flat tire case. So based here, we use a numerical fitting method to determine or to parameterize the values of A and B, and here in the expressions. And it shows clear that using these equations, it can capture the behavior of A and B very well. So for the second question, we use a coupled model recently developed by Zhang, Ge, and Yang, and all. And basically, the procedure is like this. And first, we get an initial value for the wake expansion coefficient K. Then we can use the Yates model to determine the flow inhomogeneity factor beta. With the beta determined, then we can use like a 3-layer model or the Clough model to determine the wind farm equivalent roughness height, and then we can use coupled model to determine or to update the value of the wake expression coefficient K. Then we will judge whether this interaction is converged or not. If not, then we need to iterative again. And if yes, then we add and output the wake expression coefficient and the flow inhomogeneity factor. And here is a comparison with the model prediction and the RS data, and overall the agreement is well. And for the value of AU, we derived use numerical fitting method. We learn two characters for the behavior of AU. First is when CD prime equals 0, AU should be 0. That means when there is no turbine, there is no need to correct the log law in the surface layer. And we also know that for large values of CD prime, AU will saturate and to a constant. So then with this model, we can predict that the horizontally average wind speed in the wind farm. And here the left one is for the allied wind farm, and the right one is for staggered wind farm. Okay, so from these two figures, we can see clear that the model predicts the wind speed profile here very well below the inversion layer. And because for wind energy application, we mainly focus on the turbine in swamp area. That means this model works well. So with the wind speed predict well, we can use this model to study the various effects on the wind farm power output. Here we show the effect of free atmosphere lapse rate on the wind farm power output, and the power output is calculated using this formula. Okay, we can make some conclusions from these two figures, like that the power decreases as the free atmosphere certification increases. And we also notice that the power output will reduce as the latitude reduced. That means a wind farm near to the equator will produce less power output for those close to the polar. Okay, then we can also use the model to study the effect of turbine thrust coefficient. And here we show clear that for both allied and staggered cases, the power output will first increase as the CD prime increase, and then it will reduce slightly as the CD prime continues to increase. This phenomenon is very important because it indicates that the maximum power output reaches and CD prime value different than the base limit. Thus, when we want to optimize the wind farm power output, we should optimize the wind farm as a whole, not for each single turbine. So here comes the conclusion of my talk. First, a universal wind speed profile is proposed for the CMBR flow. This model accounts for explicitly the effect of heat flux, and thus is valid throughout the underbody layer. Second, the profiles for wind component and turbulent shear stress are introduced. And these profiles are based on Ekman's equation and the universal heat flux profile. And thus, they are, and in addition, these profiles are validated by log eddy simulations and field data. Thirdly, an analytical model of extended wind farms in conventional neutral boundary layers is developed. And this model is based on the physical insights obtained from the CMBR flow and wind farm flow. And thus, the model is helpful for wind energy industry. Finally, we believe these findings may be insightful for studies of stable bottom layer and coactive bottom layer flows. Now here is a list of publications related to this talk. Before ending my talk, I want to thank my collaborators, including Professor Luoqin Liu, Associate Professor Richard Stevens, Dr. Shundi Guide, and Mr. Chao Li. Thank you very much for your attention. I would be very happy to answer any of your questions. Thank you.
Thanks for the excellent talk from Dr. Liu. So we are now would like to take practical comments and questions. So if you would like to ask a question, please just open your mic or type in the chat. Thank you. So
I have a question.
Yeah, please.
Jeffrey Jackman with Queen's University. Luoqin, mine is a simple question. Early on in the talk around the slide between slide 10 and 15, I think you defined the quantity epsilon, which was the factor in front of your pi double prime term.
In here?
Yeah, there you go.
Is it here?
And then you explained the physical significance of epsilon, but I did not understand your explanation. Could you repeat that for me?
Yes, I mean, epsilon actually, we define epsilon can be defined half of the ratio of this layer. I mean, and to this layer, and its value is about 0.12. I think is here. 0.1 is just the ratio of the inversion height to the bodily height over 2.
I see.
Yeah.
Thank you for your patience there. You're working on an important, interesting, difficult problem, Luoqin, and this was an excellent presentation. Thank you very much.
Thank you, Giacomi.
So essentially, Dr. Jackman is the editor-in-chief of POF. So maybe in the future, you can submit your work to POF as well. Any other questions?
That was my other question. I was wondering how well I had paid attention, but has this work been published or is it being prepared for publication?
Oh, this one already published in PRL.
There we go. So anyways, thank you, Kai. Sure. Future work would of course be welcome. Carry on.
So any other questions? If no, actually, I have a question here. Dr. Liu, you mentioned the vertical structure in the atmosphere boundary layer. So when these
pardon? Is a lot of vertical is vertical.
Is a lot of water. I suppose you are investigating the vertical convection, like neutral convection flows in atmosphere boundary layer. So when these vertical flow structures are important, like say, usually we talking about wind turbine, I'm thinking about like maybe just the horizontal flow will be important, but not so vertical flow. So when these vertical flow structures are important for the program.
Actually, I think both horizontal and vertical structures are important. But here we focus on, we made an assumption, and I think it's in slide 2. We focus on horizontal homogeneous case. So that's basically, I mean, in average, there's low horizontal correction only for vertical structure. And the vertical structure is very important because, I mean, like the land surface or sea surface need to exchange the mass, energy, or moisture, or water vapor to the free atmosphere. So it's very important for the balance of energy and mass, water, etc.
So essentially, it's more towards like something in the ocean, or like it's could be any torrent. I mean, also, like for instance, if atmosphere boundary layer over like city, or like atmosphere boundary layer over some forest, or like over some grass plant, like vertical structure are all important.
Yeah. Yes.
Liu Bo-se, I have another question. You have a very beautiful slide with two graphs and two equations, A equals and B equals. Comparison.
Oh, yeah. Yes.
Between theory and data.
Here?
Yeah, I think I need to see maybe the slide before this. Can you go to slide 8?
Yeah.
Okay, I'll tell you what. I'll go back to slide 9. I don't understand the physical significance of A and B.
Oh, physical meaning. And the definition of A and B is here.
I see.
Yeah.
I get it. I get it. Yeah.
Yeah.
I see.
For neutral case, it can be proved mathematically by like a asymptotical matching method. But for other cases, when some stability is basically low rigorous proof yet.
我明白. I understand. Thank you.
Thank you.
So, by the way, I am not showing my face, Mr. Chairman, because this seminar is the first one that is earlier in the morning, and I am still in my pajamas. So today I am not showing my face, just my picture. You see.
Yeah, essentially we make this seminar 1 hour earlier, like to become more friendly for Chinese audience as well.
Of course, no problem. Good idea. It's my fault, not your fault.
Yeah, thanks, Dr. Li. So if there are no questions, so I guess that's the end of today. So thanks again for Dr. Liu, and thanks everyone for attending the IBiM seminar. We'll see you sometime later. Yeah, bye.
See you next week. Bye-bye.
Bye.
See you. Bye-bye. And thank you.